Hi everyone, my name is Danielle Duvalsaint and I'm from Carnegie Mellon University. Today I'm presenting Characterizing Corruptibility of Logic Locks using ATPG, which is a work done in part by myself and Professor Blanton. So first I'll go over the introduction to this work and the motivation, and then I'll go into the background regarding hardware security, and then I'll discuss corruptibility and how we're measuring corruptibility. And then I'll go over the results of applying our corruptibility measurements to various block circuits, and then I'll conclude the talk. The increasing cost of circuit fabrication has led to many companies adopting a fabless model where their fabrication is outsourced to a third-party company. The outsourcing of fabrication to a third party allows for an uncontrolled and potentially untrusted source to access the design. This leads to an increase of threats in the design chain, such as IP theft, producing more of a fabricated circuit than a client requests, and making malicious modifications to the design, also called hardware trojans. So because of these threats, a lot of research has gone into ways to mitigate them, such as to separate fabrication for the secure and insecure portion of the design, inspecting chips post-fabrication for additional hidden components, and changing the design so that an untrusted foundry does not get the full access. Logic locking is a security method that modifies the design so that it requires the correct key for correct functionality. And so if an incorrect key is applied, the functionality of the design changes in some way. And this is done during the design stage of the device. And the key is stored in an on-chip memory that is tamper-proof, meaning that it's not observable in any way. And this memory is typically programmed post-fabrication during the packaging stage. The initial locking methods insert gates into an LS based on some heuristic. For example, random logic locking inserts XOR and XNOR gates into an LS at random locations. And so these locks result in high corruptibility, meaning that an incorrect key changes the circuit primary outputs at the higher percentage. However, these locks are vulnerable to various key extraction attacks where an adversary attempts to uncover the value of the secret key. And additionally, there are locking methods that are aiming to minimize the effectiveness of attacks by minimizing the number of incorrect keys that can be rolled out with each input pattern. And so this reduces the effectiveness of attacks that work by pruning out incorrect keys. And these locks are referred to as point function locks because they modify the output of the circuit using external circuitry. Another method of reducing the effectiveness of attacks is by inserting structures that are difficult for SAT solvers to represent. And this is done because SAT solvers are the basis for many logic locking attacks. And so, for example, LUT-lock inserts key-controlled lookup tables into a design in the place of existing gates. And then full lock, shown here, inserts a key-controlled network of switch boxes into a design. The current work in security metrics for logic locking is mainly focused on lock hardness. Lock hardness measures the difficulty of extracting the correct key from a design, and this notion has been heavily explored in the literature, with the SAT attack being an example of some of the previous work. And then key extraction attacks are typically modeled around two tools, the lock netlist and the oracle. The lock netlist is a description of the design of the locking method applied. It can be obtained through IP theft at a malicious foundry or by reverse engineering. And the oracle is the fabricated circuit with the correct key applied. This can be purchased or stolen and is used to query input patterns for correct outputs. Another metric of lock security is corruptibility. Corruptibility measures the impact that an incorrect key has on circuit functionality. Corruptibility is an important metric because if a lock does not adequately change the functionality of the circuit, then it is ineffective and an attacker can still use it when with an incorrect key. And so corruptibility has been mentioned in previous work, but it's typically measured through random simulation. And so in this work, we present a method to measure the corruptibility of a lock in a way that is scalable to large designs. And then we're also looking at two different definitions of corruptibility. So first, it's vector corruptibility, which measures the fraction of the truth table that is impacted by an incorrect key. And BitLife corruptibility looks for the number of output bits corrupted by an incorrect key. So here's an example of measuring corruptibility on a circuit with 2 inputs, 3 outputs, and a total of 4 possible key values. And so this first column shows the input pattern, while the second column shows the correct outputs when the correct key is applied. And then the last three columns show what the outputs are when an incorrect key is applied. And so for the first incorrect key here, we have a vector corruptibility of 3 out of 4 because 3 out of 4 of the rows in the truth table are corrupted. And then for the second column, we have 2 out of 4 because 2 out of 4 rows in the truth table are corrupted. And then lastly, it's 4 out of 4 because all rows are corrupted. And so this gives you an average of 0.75 for the average vector corruptibility. And then likewise for bitwise corruptibility, here we have 5 out of 12 because 5 out of 12 of the possible output bits are corrupted. And then here we have 3 out of 12 because 3 out of 12 possible output bits are corrupted. And lastly, the corruptibility is 9 out of 12. And so this makes the average bitwise corruptibility 0.47. So now I'll go on to discuss the methodology of how we are measuring corruptibility on locked circuits. To measure corruptibility, we're using ATPG, or automatic test pattern generation. And so ATPG is a tool used to generate tests to detect possible defects in a fabricated circuit. And a defect is modeled as a fault on a netlist signal line, and in particular, we're using stuck-up faults, which represents a defect where a signal line is permanently fixed at a 1 or a 0. And so the ATPG tool generates a test consisting of primary inputs for a fault which propagates the effect of that fault to one or more primary outputs. And additionally, in this work, we are using end detection, and end detect ATPG generates n distinct tests for a single fault. Corruptibility measurements are performed on the designer side, so it's assumed that the designer has access to the locked netlist and the original netlist. And so these two netlists are used to construct the miter circuit, where both the locked netlist and original netlist have the same primary inputs, and the locked netlist also has a set of key inputs. The output of the miter circuit, miter out, is 0 if the outputs of the locked netlist and the original netlist disagree. And so by targeting faults in the locked netlist that have key bits in its fan-in, ATPG generates a test that consists of a key cube and an input cube. And this is repeated n times per fault, where n is the level of end detection. And so because of the constraint placed on the ATPG tool making the circuit outputs disagree, this means that each generated test consists of a key that is incorrect and an input cube that is corrupted by that particular incorrect key. And also, we use the term key cube and input cube to refer to test patterns that have X's or do not care values. And for each generated test, the number of mismatching outputs are also stored, and this is obtained by comparing the outputs of the locked netlist and the original netlist from the generated test. After undetecting all relevant faults in a netlist, the resulting tests are arranged so that each key cube generated is associated with the input cube that it corrupts. This means that if a key cube is generated only once, then it will only have one input cube in its input list. However, if it was generated 5 times, it will have 5 inputs in its input list. Additionally, associated with each key and input pair is the number of corrupted outputs. And so the key cubes generated likely have overlapping values. So for example, in this image, the key at index 0 and the key at index 1 have overlapping values. And the same can exist in the input list. And so the next step is to remove the overlap from the generated sets. There are 2 types of overlap that we consider. So first, there's mutual overlap, where the same value exists in both key sets. And so, for example, if key 1 equals 1x1x and key 2 equals 10xx, then key 101x exists in both sets. Additionally, if one-sided overlap, if key 1 equals 01xx and key 2 equals 010x, then all patterns in key 1 exist in key 2. We have developed 2 processes to remove the overlap in the generated inputs in the keys, and these are exact counting and approximate counting. And these algorithms work by treating the keys and the inputs as sets. And so, for example, here you have the key cube 0xx, and this is equal to the key set shown here of 4 values. Then to remove overlapping sets, or the overlapping values from the sets, set operations such as set union, intersection, and difference are performed. And exact counting removes overlap without over or under counting the number of values contained in the sets. while approximate counting removes overlap by performing an underestimation of the total number of non-overlapping values. And approximate counting is less accurate, but it has a much faster runtime than exact counting. And more details on these algorithms are included in the paper. Once the overlap is removed from both the key sets and input sets, the values are used to calculate a corruptibility distribution, which estimates how corruptibility is distributed among the incorrect keys. So here we have 3 sets and 3 input lists and output lists. And so first you have the first set shows that 2 keys are corrupting 16 total input patterns. And then here you have 8 keys that are corrupting 25 total input patterns. And lastly, there are 4 keys corrupting a total of 14 input patterns. And so using this information, we can plot the distribution of the vector corruptibility. And so the x-axis shows the level of vector corruptibility ranging from 0 to 1, while the y-axis shows the total number of keys with that level of corruptibility. And additionally, using the number of mismatching outputs, we can plot the bitwise corruptibility, where the x-axis now shows what the bitwise corruptibility is for each group of keys. And so using this data, a designer can extract important information on the locks, such as the minimum corruptibility, maximum corruptibility, and the most frequently occurring corruptibility. So now I'll show the results of running our corruptibility measurements on various lock circuits. For our experimental setup, all experiments are performed on a machine running at 2.2 GHz with 1 TB of RAM. And then all ATPG runs are done using a commercial ATPG tool. And so for lock types, we're using random, lock, full lock, and TT lock. To demonstrate the accuracy of our method, we ran the corruptibility measurements on several smart benchmarks that can be exhaustively simulated to obtain the true corruptibility distribution. So in this particular experiment, we used the benchmark EX5 locked with 10 random key bits, and the true vector corruptibility is shown here. And so for exact counting, you can see that as n, which is the level of n detect for each selected fault. So as n increases, so does the accuracy of the distribution compared to exhaustive simulation. And the same trend can be seen here for approximate counting. And you can also see that approximate counting is less accurate than exact counting. However, it does still converge towards the true distribution as you increase n. So now we have the bitwise corruptibility distribution for the same circuit, EX5, locked with 10 key bits. So first we have the exact counting distributions as n increase from 32 to 512, and then also the approximate counting distributions. So as n increases, the distributions do converge more towards the exhaustive simulation distribution. However, in comparison to vector corruptibility, there is a higher level of error, which I will discuss on the next slide. The experiment was repeated for 6 small benchmarks, where the corruptibility measurements gained using exact counting and approximate counting are compared with the true corruptibility values using exhaustive simulation. So this table below shows the average percent error for both vector and bitwise corruptibility for both exact and approximate counting. So you can see that the error in bitwise corruptibility are much higher than that of vector corruptibility, where for exact counting, vector corruptibility has an error of 5.9%, while bitwise corruptibility has an error of 45.9%. And so the error in bitwise corruptibility is due to the appearance of X's in the test vectors, and this reduces the amount of mismatches that can appear in the test outputs. And so when we're looking at mismatches for the output of the test, so if the locked netlist has a value of 1, while the unlocked netlist has a value of X, we cannot conclude that 1 and X are a mismatch. Same for like 0x. So we can only look at mismatches if they are 1, 0, or 0, 1. And so because of this, we do have a higher level of error in the bitwise corruptibility. In addition to the small netlist results, we also ran the method on large netlists to demonstrate scalability. And so for these netlists, we use scanned versions of the GPS and DES circuit from the Common Evaluation Platform, and also a scanned version of the NC from the OpenSpark T2 processor. And then for random lock and TT lock, we use lock sizes of 64 and 128 key bits. And then for full lock, we use lock sizes of 64 and 176 qubits. So here we have the results of applying our corruptibility measurements across all possible input patterns for all 4 lock types. So on the x-axis, we have vector corruptibility. On the y-axis, we have bitwise corruptibility. And for both, we're plotting the average obtained for each lock type and key size. And so on average, you can see that LUT-lock and random provide the most level of corruptibility, while on the other end of the spectrum, TT-lock provides the least corruptibility. And so random and LUT-lock provide the most corruptibility because the effect of the lock is more spread out within the circuit. Well, for TT-lock, the effect of the lock is focused on corrupting only a small subset of input patterns. And then full lock falls in the middle because the structure of the Blanton network is more centered on corrupting a subsection of the circuit. We also looked at corruptibility for a specific workload for both the DES and AES lock circuits. And so for these measurements, the workload is considered the input and output patterns that are part of the functional usage of the device. And so this measurement captures the error that an adversary would observe running the device in functional mode with an incorrect key. And on average, random locking and LUT locking still achieve the highest level of corruptibility, while TT lock still had the lowest level of corruptibility. So overall, corruptibility is an important metric that needs to be considered in lock design, along with other metrics such as lock hardness. And so corruptibility is measurable on large netlists using ATPG, as we've shown in our experiments. And other versions of corruptibility, such as workload corruptibility, are also measurable. And so our future work is focused on measuring corruptibility on sequential non-scan designs. So thank you so much for listening to my presentation, and please feel free to contact me if you have any questions.